this calculation provide deeper insights into material properties, surface characteristics, and chemical states of the elements involved? What are the challenges and limitations of accurately measuring EC in real-world XPS experiments, and how can these challenges affect the calculation of EB? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the precision of this calculation influence the interpretation of XPS spectra and the analysis of different materials? How do variations in the energy of incident photons impact the results of binding energy calculations in XPS experiments, and what does this mean for the accuracy of material analysis? How can the accuracy of binding energy EB calculation in XPS be improved? What is the work function phi s, and how does it influence the calculation of EB? Why is the recoil energy air significant when considering the radiation process, and how does it affect the accuracy of EB calculations? How do the work function phi s and recoil energy air play a role in refining the measurement of binding energy in XPS? Why is it important to account for both the work function and recoil energy when aiming to achieve precise results in the XPS analysis? How does the inclusion of the work function phi s alter the overall binding energy calculation, and why is it necessary to include this factor? What does recoil energy air contribute to the understanding of energy shifts in the XPS spectra, and how does it impact the interpretation of electronscape dynamics? How do the factors of phi s and air contribute to a more accurate representation of the energy changes that occur during the photoemission process? What mathematical adjustments must be made to incorporate the effects of phi s and air into the calculation of EB, and how do these adjustments improve the accuracy of the data? In what ways does considering phi s and air help to refine the measurement of electron kinetic energy and improve the determination of binding energy in XPS? How can the combination of these additional factors lead to a better understanding of the material's electronic properties? How do phi s and air interact with the other parameters, such as the incident photon energy, to provide a more comprehensive analysis of surface chemistry in XPS? What challenges might arise when accounting for phi s and air in binding energy calculations, and how can these challenges be overcome in practice? How do these refinements improve the precision of XPS measurements in real-world applications, especially in the analysis of complex materials? How can researchers apply this more accurate method to achieve better material characterization and surface analysis? How does this approach help mitigate systematic errors in XPS experiments that could otherwise skew the binding energy measurements? How does the chemical environment of an atom affect its electronic binding energy B in XPS?